Yeah. Yeah. So I guess the only reason. So that I have an introduction slide for Circus, okay. and then we'll just we can get started.
Hello, everyone. Welcome to the Circus Seminar Series. Circus is the Center for Research on Computation and Society at the Harvard School of Engineering and Applied Sciences. It brings together computer scientists and scholars from a broad range of fields to make advances in computing research that serves public interests. Circus is directed by Milind Tambe, who is Gordon McKay Professor of Computer Science at Harvard CRCS, and also a principal scientist and director of AI for Social Good at Google Research. In addition to the seminar series, we hold other special events such as workshops and panels. You can keep up with these on our social website or Twitter. We also hold postdoctoral fellows and summer fellows. Please note that we're currently accepting applications for 2023 postdoctoral fellows. The link is at the bottom of the slide. Coming to today's seminar, Circus aims to design tools that center equity and sustainable deployment, and this seminar series is an opportunity to engage with and learn from a diverse set of perspectives on how to achieve this mission. This week, we have invited Professor Conrad Tucker, Arthur Hammerschlag Career Development Professor of Mechanical Engineering at Carnegie Mellon University. His research focuses on employing machine learning and AI techniques to enhance the novelty and efficiency of engineered systems. His research also explores the challenges of bias and exploitability of AI systems and the potential impacts on people and society. He is currently serving as a commissioner on the U.S. Chamber of Commerce Artificial Intelligence Commission on Competitiveness, Inclusion, and Innovation. Professor Tucker received his PhD, MS, and MBA degrees from UIUC and his BS in Mechanical Engineering from Rose-Hulman Institute of Technology. Thank you very much. I will hand it over to Professor Tucker.
All right. Thank you very much, and good morning, everyone. This is going to be very interactive, so good morning, everyone. All right, thank you. We're going to do a switch here. Please feel free to ask questions. I'm going to ask you questions. I would like this to be a conversation rather than just me talking for an hour. And so as we get started, I just want to, first of all, thank Professor Milind Tambe for the invitation, and really to thank the multidisciplinary aspect of the center, because I think the interesting and challenging questions that we have as society are multidisciplinary. So I'd like to start with acknowledging my team. So this work extends beyond just me. We have a team at CMU that even has extended beyond the team you see here, and also acknowledge our funding agency, the Bill and Melinda Gates Foundation, for a lot of the work that I'll show here. So the vision of this dimension of my research is really to take the algorithms that we develop in the lab and deploy it in communities in resource-constrained environments. And so when I speak of communities, I'm really talking about the communities at the very most need in society, and the constraints that we therefore build around our algorithms are constrained with our individuals in society in mind. And so the challenge that we have observed through this journey, so I was never an experimental scientist that was doing work in the field, but the challenge was given to me by a funding agency to see how well our algorithms deploy in the field. And so really this is this kind of challenge or mismatch where many of the individuals who are designing these algorithms are disconnected both geographically and even from an understanding of what the problem is. And that presents several challenges, such as the assumption that everyone has internet, that you could just turn on your phone and you have 4G connectivity. It turns out that's not how it is in most of the world. For example, the demographic distribution and the places that algorithms are developed and the places that they're deployed are quite similar, or even just the generalizability. So we have one use case, we demonstrate nice, we publish a journal paper or a conference paper, and that is meant to generalize across the world. So we primarily are focusing on using devices that have become quite ubiquitous in society. So I'm not talking about some high-end $1,000 phone. I'm talking about a phone that you can buy in resource-constrained environments that cost less than $100 or even less in some cases. And so what we want to do is to explore how much we can develop algorithms using the single mobile device. It's a great data collection device. So there are two approaches. Once you acquire data, either there's a theoretical driven approach where you're basing your algorithms on first principles to come up with algorithms and insights, or the very nice, fancy approach that's become very prevalent in our scientific community are some data-driven black box model like a neural network, and you're just going from data to some label, and with enough data, you're able to get very high performances. So I'm going to talk about the pros and cons of each of these approaches, but really starting off with the first principles theoretic based approaches. So this is going to be the first kind of audience participation for the day. So one of the from a medical point of view, vital signs are absolutely critical. And before I show you what the algorithm that we've developed actually does, I want you to turn to your closest neighbor and, first of all, if you don't know them, introduce yourselves. And then just stare at them for 30 seconds and see if you can tell me what their heart rate is and their temperature, if they have a fever. So just, I'll wait. Just turn and stare at them. Just vision-based approach. And I want two values. How fast is their heart beating? And do they have a temperature or fever? Just looking at them, not... And you can't ask them from their smartwatch to read your value, which I see some very creative solutions from the audience. All right, who wants to volunteer? Who can predict? We always need ground truth. So I appreciate the fact that some people have the ground truth from their devices. I saw a very engaging. Did you? How close were you to the prediction? Yes.
I think I was pretty close, but maybe me staring at her made it raise a little.
That's very true. Intervention changes the outcome. Who else was plus or minus 5 BPM? No one? Okay, so that's in essence what we're trying to have an algorithm do. So using just a vision-based technique, again, we deliberately constrain with a phone and deliberately constrain with video data to extract signals that exist in the data capturing devices that we have. And so this is one example of, you may have seen some of these algorithms where you have just video data, you're able to magnify the pixels of this. I know that it's hard to see, but if we turn the light off here, so this is a slow motion and magnified from the color domain. What you would see is, if you look at from frame to frame, there are very slight changes in the pixels of that particular skin. And this even works in darker skin individuals. So it's really agnostic to the skin composition. All you're looking for is a difference in that pixel. And with that difference, what you're able to then do is make approximations about different vital signs, such as pulse rate. So over time, you're able to look at these differences, and using signal processing techniques, you're able to map this into the frequency domain and really get a sense of what is the frequency of a particular heart rate at a particular, for a given individual. And you're able to do this in real time. So this is an example of the algorithm overlaid on different demographics and being able to get the running average of the beats per minute for a wide range of individuals. So the three kind of rectangles that you see here, these are the regions that are being used to extract these signals. So here's another quiz. Why these three regions? Who can guess or make an inference? Yes?
Probably where blood flows closest to the skin.
Blood flows closest to the skin. So one hypothesis. Any other? Why are we? This is very important because it ties back to our field deployment, and we'll see why shortly.
Isn't that kind of where some coloring comes from? So that's where you'll see like flashes in the cheeks.
Okay, so flashes of the cheeks, definitely there's coloring in certain regions more so than others.
It's hard to emotions.
We haven't deployed emotions yet, but you could take, let's say, the key points and map that to certain perceived emotions, right? Because the only person that has the ground truth for the emotions is the person themselves. So just because someone smiles doesn't necessarily mean that they're happy. So you could map emotions as well.
No hair.
So we don't have as many artifacts in these particular regions. So if we're looking for the least polluted signal, we want to identify regions that they may not have as much occlusion. Was there any? Okay, so these three regions are selected because of those characteristics that we've looked at there. And with that, you're able to then deploy these algorithms to make these inferences. So this, video-based pulse rate is a very active area across both industry and industrial research. One of the kind of the newer works where we have this paper under review was actually motivated by our real-world field studies. Because if you are in a community that maybe does not have access to a high-end thermometer, but they do have a phone, the question is, can we make other inferences about other vital signs, such as temperature, without the need of another specialized gadget? What do you think? Sounds hard, right? Well, it's extremely challenging to do this without an infrared camera. So what we're doing is exploiting some principles of the recording device and the way that light interacts with skin to come up with a classifier for determining elevated temperature versus not. So just really quick about the different ways that light interacts with materials and surfaces. The light can bounce off, it can refract, it can scatter in these different materials. You can think of the skin as one type of material that we have light, whether or not the light is artificial or from the sun, interacting with our skin. So we want to use these principles of how light interacts with skin or different materials to see if we can make an inference about, does someone have an elevated temperature without the use of an infrared camera? Again, we deliberately constrain with what people have, which is a cell phone. So the naive way to do this would be, okay, well, we're just going to, we have a measurement device, let's say the camera here. We measure how much light bounces off, and we measure. And if only the world worked where if someone has an elevated temperature, this is different, right? Then perfect. It turns out that it's not that easy, because when you look at reflection of elevated skin and non, you cannot just do that with an RGB camera. There are many thermodynamic principles and the way that radiation emits that we cannot just use the camera to just measure reflectance. So what we can do, which is actually a flaw in every camera device, whether or not it's an infrared camera or an RGB camera, is that if you're observing a person or a surface and the angle of that surface changes, there are actually some the error in the reading that you're getting. So imagine someone has a temperature. Based on how you turn your head, should that temperature change? Right? So the ground truth, it doesn't change, right? But the measurement device that's observing the rotation of someone's head gives very slight differences in the temperature reading. So it's almost like an error in measurement devices that we're exploiting to come up with this approximation. And so this is an example where we use just as a validation the thermal camera, and the thermal camera of this, the temperature of this person's skin when they just slightly tilt their head has these differences, even though the temperature actually is the same. So based on this difference, we now have a ratio of temperature observed at one angle, temperature observed at another angle, and that actually has a relationship with this reflectance principle that we just talked about earlier. So what we then are trying to do is someone is looking at a camera. It could be any two angles, and based on that difference, you're then able to create this binary classifier that's able to determine elevated temperature versus not. Now, again, it's important to highlight that because we do not have a thermal camera, we're not able to provide the absolute temperature. But what we are able to do is, using just vision, determine if someone is feverish or has an elevated temperature. So this is my PhD student. He's the first author of this paper. But in essence, we want to then not only come up with the algorithm, but experimentally validate the performance of this algorithm using a ground truth, and seeing what a lot of different people and seeing what the performance is. Now, for those who are in the social science, how many people have worked on IRBs or know what an IRB is? Okay. What would be some of the IRB? So IRB, for those who are institutional review board, if you're ever doing an ethics study or a human or biological species, you have to make sure that what you're doing is ethically sound before you conduct the study. So it's a long process, but it just makes sure that as scientists, we're doing the right thing. Now, for those who have engaged in writing an IRB or reviewing, what are some of the challenges you would see trying to experimentally validate if this algorithm works? Yes?
That's the question of how you're inducing that elevated temperature. Like, are you just like giving people flu virus?
We're giving them COVID. Let's or some other virus that elevates. Would you want to engage in that? I would be terrified. Even if the IRB approved that, I would be terrified to conduct this experiment where you are medically inducing the body's response that then creates increased temperature just so that you can prove an algorithm works. Any other? So if we're not doing that, what would you recommend? Yes?
I guess another problem is that the devices are often tested in ideal situations, like right now in this room versus in hospital settings or ICU settings, where it might be hard depending actually on whether it's a...
Yes. So it turns out when your temperature is elevated, you're not feeling too good. So now we're going to say, sick patient, please sit in front of this device, and we are going to capture your temperature. And then when do you even capture their temperature at the baseline, right? You're trying to compare the elevated versus not. So even if you could recruit a participant pool with an elevated temperature, you'd have to either wait before when they were at a baseline and when they had an elevated temperature, or again, find some way to induce it. So any other concerns to do this study?
Be afflicted by the people who are sick.
So now, as a researcher, I am in the environment where whatever pathogen that's creating this temperature change, I'm now at risk, right? So there are all of these different challenges from going from the algorithm development to the experimental validation of these algorithms that present all of these challenges. And this is just in the perfect lab. We haven't even talked about deploying this halfway across the world in these societal differences and cultural differences. So what would you recommend? How would we be able to have a temperature difference without making people sick? Yes?
Have them work out a bit?
It turns out the body is a very good temperature regulator.
Really?
Yes. It's then you have other artifacts like sweat that then create these challenges. And
But you sweat even when you are sick, right?
that's true. So we're staying away from sick people. So we were not doing staying. Yes. Yeah. Either. Both. Who wants to go first?
Maybe if you collect a lot of data on these sick patients, like biomarkers or like temperature, maybe you can build a simulator that would simulate patients' temperature in different environments. So then you can do it all with code. I know it's not so
All with code. I see. Got the. Are you a computer scientist? I know. They just always say, just do everything with code. We could create a. In fact, I don't know if you know there's like a meta-human data set, and these they're like digital humans. And it turns out that the way that they've modeled the skin in these digital humans is actually quite comparable to the real. And we tested the algorithm on digital humans, but it still presents the challenge of how do you, even if it's with code, how do you know the properties of human skin when it is outside of the baseline? Yes?
Reduce the temperature. Reduce the temperature, like cool them. Put them in the freezer.
Put them in the freezer. I'm going to hand over my research to you, so continue. All right, we have put them in the freezer, make them sick. Whatever.
What about a sauna?
Okay, so now we're now on vacation. We were going to send them to a vacation. Yeah, so we could. So now we're going back to inducing. How would you walk me through the IRB for this? What would you? Let's not just theorize. What would you do? So recruiting. What is your recruiting flyer for someone to sign up?
And this is like really putting me on the spot because
okay.
I do a lot of work with IRBs.
All right.
So you have the study, a little, like one sentence about the study.
Okay.
And you have a picture of a sauna. I don't know.
And you tell people.
We're gonna take your temperature first, and then when you get here, and then you're gonna sit in the sauna for, I don't know how long you sit in the sauna for.
Okay.
And then we take your temperature again. And the purpose of the study is to see if our algorithm is to validate our algorithm.
All right. So how much would they have to pay you when you read that flyer while sitting in a sauna to sign up for that? Pick a number. How many dollars?
It's like less than an hour.
Right. I'm very protective of my data, so probably not.
Pick a number. She has to write a proposal to get funding to do the study. So what is the number? $1,000. Oh my God! So you need to have enough data sets to come up with generalization. You're paying $1,000 per person.
How about if we study people who get vaccines that we know induce fever?
Okay, so we're recruiting people that
Just get vaccinated,
just got vaccinated, and if that person collapses while you're responsible, right?
No. People that anyway will get the vaccine. You don't force them. So you set up a booth in a hospital.
It takes a couple of days to get
The fever?
the fever.
But even if they do, so you're still
The COVID vaccine, like the same evening I was.
same. But the question is, and it may just be correlation that they happen to pass out while you're doing the study, right? You didn't cause it. Would you want to take that risk as a researcher to have?
No, but I wouldn't take the
Oh,
vaccine,
no.
right?
Huh?
Just
I'm
there
just
observing.
there. I'm just there. I know. I'm not responsible.
You're not there. Tell them how the IRB works. Unfortunately, you have to assume responsibility for the safety and the care of your study population. Right. Yeah.
So what if they monitor themselves? So like they have like wearables so that like, I don't know, like every time their body temperature is like or facial temperature is elevated, it like automatically maps to the image.
Are these normal people, healthy people that you now have like, what was it, like a year's worth of just baseline, they're normal, and one day when they have a temperature, you want them to run. So you could. Expensive, yes.
If I differentiate between people well enough, then this might also hold, right?
You mean just baseline?
Take a lot of people, and if I differentiate well, then the algorithm works.
I see. So again, this goes back to since it's a non-IR approach, we are unable to get the absolute temperature. So it's just a binary classifier that's able to. So you need to have some ground truth of elevated temperature in the data set. So how do we get that? In the back, then we'll come.
I feel like in order to get a label, it's almost like we need to be in a clinical setting where someone that we rely on can give the label. So like partnering with like primary care practices, because they will see a wide range of people just coming to like refill your prescription, you're not sick, or like someone who has an acute event. And so you'll still have a wide range, but you'll have a clinician who can actually annotate and say 1 or 0, and you're more likely to trust this person than to trust someone who just reports whether I think I have elevated temperature. And also they can ask questions like, they can annotate properties of the skin. For females, we know that hormonal changes can also affect temperature measurements, so the doctor is maybe better suited to annotate that.
Yeah, so now this motivates doctors and engineers and computer scientists working together. Turns out that maybe the time to get all these people together may be even doctors are busy saving lives, and just finding that time for them to also do this as well. Along those lines. So what did we do? It turns out your idea was not that far off. So we didn't use a sauna. However, we used a heat lamp that actually, and even this, I mean, it took a while for the IRB to say, well, how much are you elevating their skin? Is there a risk of them passing out because of it's a risk minimization, but the risk isn't 0. It's very hard for that to be. So this is the experimental setup. Even things such as, and the reason why this is important is because imagine trying to replicate this in a village or somewhere halfway across the world where you're trying to explain or set up the experiment so that it's identical to these conditions. So you'd say, okay, well, just how do you explain someone to turn your head? Seems pretty easy, right? Until people are not turning their head as much. So we literally have to put markers to say, turn your head at these waypoints in this order, so that you're able to get the geometric diversity that you need for this. And then you have the heat lamp that induces this artificial heating of the skin. Then you're able to get this before and after ground truth. So we call this the normal and elevated skin temperature data set. In our work, we also, not only the algorithms, we also open source the data sets so that other teams can validate. We're in the process of wrapping up one of the largest data collection in the world is 2,000 participants, 1,000 from India and 1,000 from Sierra Leone, who replicated this process in those countries. There was a hand here, or yes?
Does it matter that the heat lamp's only on one side? Like in your data set, did you get higher temperatures on one side?
That's a great question. So first of all, the reason why we couldn't put it right here is because then the measurement device itself would be obscured. But the way we overcame this problem is during the heating of the face, the participant would stare directly into the heat lamp and heat for a few minutes and then go back and rotate.
Gotcha.
Yes?
In practice, would it be hard to differentiate between individuals who are like in the sun for too long versus have a fever with like the
We thought about the sun, but then we're trying to control all the variables, and so that would be, and so this would be kind of like in the wild being able to start, which we also, I'll show you in the next slide, how beyond the lab setting, we're also able to validate in more unrestricted environments. Yes.
Do you ensure that the vision algorithm isn't just picking up on the light and is actually the light on the face and is actually picking up on the heat?
So it's not picking, okay, so yeah, so we're not using an infrared, and really what we're looking at is just the difference in the pixel intensities. So even if there's a light source, the light source is consistent, and given the consistency, we're still looking at the difference in the pixel.
Can you just remind me why we're doing this? Because is the current method of taking temperature from patients not good enough, or why are we trying to do this?
We want anyone with a phone in a village without a medical person to be able to capture vital signs that quantitatively are consistent across different populations. And so that standardization is what we're trying to do. And yes, a $20 IR camera measurement device may be accessible here, but asking someone in a village beyond the phone that they have to start having these medical devices is what we're trying to mitigate. So, yeah.
Sorry, I'm just wondering about these last two techniques you showed. Did you test if they are robust to all of these computational photography algorithms that all of these companies put in the phones these days? Like if you switch from phone to phone, do these still work?
Great. So we do have a study. So I'm going to show when we varied across different resolutions and even the color spectrum. So you could measure light in RGB. You could separate these channels, and you can see the differences in the performance. So I'll show that here shortly. But to your point of, well, what is the performance of this? So we first did this in the lab, and then we also took, so the question, where are you going to get actual people that have temperature? So we relied on, so during COVID, people would have these YouTube videos. I have COVID, they have a thermometer that they measure themselves. People post everything online these days. So we have a data set that was curated where the ground truth is provided by people that actually have elevated temperature. And that was so these data sets were from this environment. And so the F1 score that we're getting from this data set right now is at 0.8. It varies, but it's around 0.8 given the environment. And so again, the person turns their head. All you need are two angles, and you'll be able to classify this. So great, we have a lab. Now the hard part. Well, that was hard as well, but now the even harder part. So going from the lab to the field, we then, I had never done software development. I was always in the lab. Now we're writing apps or getting teams to help us write apps. That by itself could be an entire talk of just the challenges of communicating what your specifications are to what people want. So we have this ground truth device. This is the app that we had a developer make for us in collaboration. And then we have these field studies. So these are ASHA workers in Bangalore. And the first thing we have to do is have some ground truth device to see how well these algorithms compare with FDA approved. So this is an FDA approved pulse oximeter that has multiple other measurements. We have and simultaneously synchronized the time, so we're able to see what the performance difference is in different demographics. So India and Sierra Leone are the two kind of main data collection sites that we have. And again, we repeated the study in these two sites. So now we go to, this goes to your point, the variability problem. There are variability in the algorithms themselves, the people, the environments that they're collected in. So let's start with the real world context. So I just haven't found a way to avoid, if you really want to solve and understand the problem, you have to be there. So I don't know if this is hard, but this is me in a village in Sierra Leone, no access to internet and running water. But if you look at the house behind, like if we really want these to work, like this house with low lighting or the luminance of the bulb there is different from this nicely lit, this is the robustness we want to demonstrate, and this is really where we want to go if we want to have this kind of translational research. And why? So here's showing you just, yes?
Just curious, how come they have phones if they don't have any internet?
That's an excellent question. It turns out that, I don't know, phones, you will find a phone in a village before you find indoor plumbing. And it's just revolutionized just the access to way people communicate. And so it's primarily used as a communication device. But because, yeah, so peer-to-peer, I mean, like just a normal cell phone talking, text. Mostly it's WhatsApp has become like the international standard. And because they have these devices, again, we're not talking about fancy bells and whistles. We're talking about, you know, low-cost Android, primarily Android devices. That's why. And that was one of our surprises as well, is that you would go to these remote areas and there would be a phone and maybe not even running water. And so when you look at the algorithms in these environments, the reason why even just understanding the variability when you change an algorithm, these are two different algorithms. So DLib is a computer vision way of detecting someone's face. This Z-face is a more recent. It uses it simultaneously trains on the 2D video and a depth to get a more robust approximation of someone's face. So let's look at the differences. So same person, before you can even employ these algorithms, you have to determine what is a face. And you can see, like we can see that this is a face, right? But algorithms struggle in even detecting this person. So this one algorithm, and this is widely used in CV community, 1% of the time it was able to detect this participant's, the existence of their face. And the other algorithm is half the time, but it's still not that great. And the question is, well, why is this happening? If you can't even detect someone's face, all the upstream or the downstream algorithms that we just talked about are very difficult. So just to show you the difference of this algorithm that works a little better and the other one, this is simultaneously training on depth data and vision and RGB, and it's able to get a more robust estimation of someone's face. So let's see from your, and you can actually create a 3D mesh of someone's face just from this 2D video. So when you look at these two geometries, can you tell me which is from what part of the world? So Africa or India? Let me show you again. Which is the face from Sierra Leone, which is a face from India? Let's get a vote. So who thinks this is from India? From Sierra Leone? Who can't tell? Okay. So if you said this is from Sierra Leone, you're right. This is a lady from Sierra Leone. So you can start seeing even the geometry of faces impacts the way that, if you look at those algorithms, if you're extracting signals here, the way that someone's topology is shaped can actually impact the performance of the algorithms, or even for that temperature, the way that the light bounces off. All of these differences have to at least be considered in the observation. And we can see the measurable differences in the performance of these two algorithms where we applied on these data sets from India and Sierra Leone, and just changing the face detection algorithm from DLib to Z-face gives considerable performance differences. but they're still not perfect. And so randomly sample, so this is 30 people, so this represents the people from India and Sierra Leone and India. You can see here that person 21, this is a huge problem for this algorithm. It's like the person doesn't exist, right? The number of missed frames is almost equal to the number of total frames. When we change the algorithm, it's most of it gets better. So this is from the dlib to the z-face. The yellow goes down. But still, this person, 21, is almost not seen. And as researchers, this then, at least for us, motivates why we need to have these real-world deployments that can actually motivate some new foundational algorithms that help to identify person 21. And it doesn't have to be this tension of either or in terms of research. Yes?
I was just wondering, like, it seems like it doesn't work well when there's like low light conditions, but can you not use like the flash on the phone to help make up for that?
So in some cases you can use artificial light, but even the artificial light creates sources of variability that may also be difficult to measure. And that goes back to your question of different phones have different luminance of the flashlight. And if you can't control for that, you may be also introducing another source of bias.
Do you have an explanation for why person 21 was never able, like, could a human looking at the video be able to understand what's going on there?
Yeah, so in the same way that we saw the participant from India, where we as humans could know that there's a person, it's really about the shadowing and lighting and the way that these algorithms entrain. In fact, that's exactly what this variability in people, where if you look at these, and this is why I showed, you can either use a first principles approach, or you just end-to-end. You have data, you have a neural network, you have labels. This is an example of, to your point, of for these face detection algorithms trained in many times in universities with age demographics, and here's the challenge. Okay, so when people make the case for why do we need diverse data sets, I mean, you're starting to see that from a technical point of view, it's in everyone's interest, even from a for-profit company. It's in their interest for their algorithms to work as robustly across different demographics to be adopted. So these are some of the challenges in the data sets. And so this is how we want to revise these data sets that algorithms are used to train on. I go back to those regions of interest, which now come into question here. Remember, we're taking these 3 regions of interest, let's say the cheeks. There are certain cultures that have cultural markings. And if you're averaging the pixels in certain regions, now you may have introduced other sources of bias that may not be in different populations. The place this comes in, if you're trying to compare across different demographics, you want to at least be aware of these different artifacts when you try to compare across places. Yeah.
So that means that in terms of cultures, like Western cultures that were made up, your subjects are asked not to, right? Something like that. I mean, these are cultural, so there's different, but kind of like the main line here that we don't tend to have artifacts in our face, that maybe make up, that would kind of throw us off.
Well, the good thing is, since we're just looking at the difference in the pixel, even wearing makeup creates a difference. The challenge is if some places don't wear makeup, or if there's certain regions that have certain features that are distinct to that culture, and we're trying to generalize across different demographics, that's where some of these risks emerge. Yes.
What about Botox? Would that affect?
It would affect, so going back to the algorithm that uses the light reflectance, the geometry of someone's face may definitely impact the way that the light reflects from someone's face. So these are all sources of variability that we want to take into account. And even for the ground truth device, so we have these two environments, but the ground truth device itself is where we start to say what are the differences. So we want to have this baseline so that when we're comparing different algorithms, we know how the ground truth works. So this study, which is also led by my PhD student, is looking at the ground truth device. We want to look at the sensor, the signal, but there are all these sources of noise. And so first starting off with what is just the manufacturer reported error for estimating these vital signs. So this would come in if we were varying the measurement device, which we weren't. But at least we want to be aware that the measurement device itself, the ground truth, has variability. These are the two regions that we collected data, so Sierra Leone and India. At least for the time we collected it, the temperature and conditions and weather conditions were similar. But imagine you were collecting data in India and somewhere up north where these weather effects may also be different. So we wanted to test we wanted to do a series of hypotheses tests just to see what the mean distribution of pulse rate is in different countries as the baseline for the measurement device. So test, is there a difference in just the average population? Are there gender differences in pulse rate? Are there differences in the mean pulse rate when it comes to, I think this is, so gender, male and female, and also age differences, and finally skin tone. So going back to, we're able to partition skin tone into these different color channels, and are there differences in the skin composition in demographics in India and Sierra Leone? Yes, there are differences when you look at populations in India and Sierra Leone, but if there were differences within country, then that would have created additional challenges when trying to generalize. But in this case, at least, within country, there weren't differences in the skin tone. So in summary, when we benchmarked all these data sets, deep learning based, non-deep learning based, looked at how they compared to the ground truth data. So the Massimo, the green, is the FDA-approved device, and then the red is one of the video-based algorithms. So we saw that for many, once deployed in these diverse regions, if this is the Massimo device that found this significant difference in India and Sierra Leone, many of the algorithms that we compared were not consistent in the ground truth device. And again, in summary, to why that may be, many of these algorithms are tested and deployed in lab environments. So hopefully I've made the case. I know I'm preaching to the choir as to why we need to have more engagement with the communities that we want to serve. This has actually motivated our lab and others to kind of think of digital health in this global context where we have partners around the world. I was just in Kigali last week where we were looking at, well, what comes next in different demographics, and how can we create this sustained network of data collectors and individuals who help inform how our algorithms are developing. So I would like to take this time to acknowledge our collaborators. Again, this goes from our colleagues on the ground that are actually healthcare workers, all the way to ministries that provide us the approval. So with that, thank you very much for your audience, and I'll look forward to any other questions. Thank you.
Yeah. Thank you so much for the talk. This is so interesting and very engaging. I'm curious to hear your thoughts about what goes after. Even if you have a really good algorithm that can detect temperature, in these resource-constrained environments, I can imagine it to be really hard to really send out resources to help people who might have those without the other part, how can you? Yeah, I'm
agree.
curious to hear your thoughts.
Wow, he wants to do everything. It's not enough doing. No, it's a valid point. What comes after? This is the intervention part, and also the measurement of the intervention. And my hope is that there are esteemed colleagues here that also are part of this this journey. But it's been hard enough just to, again, we're working on the fundamental algorithm development and also the deployment in the field. Our next stage would be what happens when there's an intervention or even the challenge of getting to these communities. In Rwanda, I was just speaking to the head of the Rwanda Space Agency, so where they're using, Zipline, it's like a drone organization that's delivering like blood samples and other in very hard to reach areas. So that absolutely has to be part of a very big part of the pipeline, the intervention, and hopefully there we can have more people that are part of this network.
Thank you so much for the talk. I really enjoyed it, and I like how practical your thoughts were and the fact that you engaged the audience. So thank you for that. I had a question about the delta in the directionality of reflectance. Like, how does that translate to temperature? How much of a temperature change are you able to detect? And I'm asking this specifically because if you're trying to detect temperature changes in a village, for example, like what range of diseases would you potentially be able to like say, oh, is it a fever or a flu or something of the sort? So what's the range you are able to identify?
Well, we're using a medical threshold for the temperature at which, from a medical definition, is classified as feverish. But the actual absolute temperature, again, it is something that is an unsolved problem because we're using an RGB and non-thermal. So the best we can do now is to use that medical threshold of, based on the differences observed when someone turns their head, is that classified as being elevated, an elevated temperature. That classification, to your point, needs to then be linked with a particular disease state or some type of intervention, which hopefully comes.
Yeah, I think I get what you're saying. I'm just not clear still. So what is that elevated threshold? Like, what is the medical definition?
Yeah, it's a specific Fahrenheit value of if it's above like 99 or 100 degree Fahrenheit, that is classified as a low-level fever or high-level fever. So we're using the medical. Again, these are, even from the medical sense, this is like an empirical derived based on years of expert insights. And it turns out, I mean, I've learned so much in this medical field just doing this work. It turns out even what it means to have our normal temperature were based on studies in the European context, like in the early 1900s. And that's used as a global definition of what the baseline body temperature is, right? But I'm not aware of a study that's gone to every community to just measure what the baseline body temperature. And so this, even to create a data set, is an opportunity where just getting a baseline of a temperature could. Seems like we need a lot of funding to do all the things that you guys do.
I think we've done very good work. I think my question was just to understand what the model is doing. So after you take the pictures, do you tell the person you have an elevated temperature or you don't?
Yes.
That's what the binary classifier.
That's what the binary classifier. But beyond that, linking that to a particular disease state is something that we have not done yet.
Okay, thank you.
So difficult just to take the body temperature. How would you extend that? Would you consider extending that to other, like using voice or?
Yeah. So if I go back to just at the beginning where you have this device that you're trying to extract these signals, you can use multiple signals that are captured by the device to maybe enhance the robustness of a classification. So I think there's absolutely an opportunity to not, and there are groups that are using, let's say, the way that the frequency or intensity of a cough as a classification for the existence of COVID or some disease. And so there are already teams that are doing multimodal sensing. We've just focused on video-based for now.
Thank you so much for your presentation. It was super interesting. I really enjoyed also how you shared this close work with the communities and where you actually want to deploy your model. I'm also very curious to hear about your perhaps like collaborations or partnerships with, I guess, like people in the medical field or like clinicians, because I'm assuming that, for example, thinking of the reflection of light as a proxy to understand temperature level, that's something that must have came from conversations with people in the medical field. So yeah, very curious to hear as to how this conversation.
So our experience, and maybe this is different here, is that collaborations with medical researchers is absolutely needed to kind of scale these projects, but it's our